Welcome all. Now we are going to discuss Theorem 10.3. For that we need some definitions. The concept of a projection. Okay. What is a projection? Let X be a linear space. A linear map P from X to X is called a projection if P square equals P. Okay. So this is the definition of a projection. Then there are some results connecting with this. If P is a projection, then the first result is I minus P is a projection. Okay, where I is the identity map from X to X. Okay, here is the proof. We have P from X to X and P square equal to P, and I from X to X, which is the identity map. Then to show I minus P is a projection, we need only to show that I minus P whole square is equal to I minus P. Clearly I minus P is a function from X to X, and I minus P whole square is equal to I square minus 2IP plus P square, which is equal to I minus 2P plus P, since P square is equal to P. This means that I minus P whole square is equal to I minus P, and hence it is a projection. Okay, and the second one is R of P is equal to Z of I minus P. That is, the range space of P is equal to the zero space of I minus P. Okay. For that we need to show that R of P is a subset of Z of I minus P, and Z of I minus P is a subset of R of P. The proof is here. If we choose Y element of R of P, then it means that Y is equal to P of X for some X element of X, since it is an element of the range space. Okay. Then I minus P of Y is equal to I of Y minus P of Y, which is equal to Y minus P of X, because Y is equal to P of X, and this becomes Y minus P square of X, and since P square is equal to P, this becomes Y minus P of X, and P of X is again Y, so this becomes equals 0. This means that the point Y is an element of Z of I minus P. Okay, so we have R of P is a subset of Z of I minus P. Again, let X element of Z of I minus P. This means that I minus P of X is equal to 0, and so I of X minus P of X is equal to 0. This means that X minus P of X is equal to 0 means P of X is equal to X. This implies X is an element of the range space of P, and hence Z of I minus P is a subset of R of P. From this together, we can see that Z of I minus P is equal to R of P. Again, the third result is Z of P is equal to R of I minus P. Okay, that is, the zero space of P is equal to range space of I minus P. The proof is as similar to that one in the above. Okay, so we are proving R of I minus P is a subset of Z of P, and Z of P is a subset of R of I minus P. Next, the fourth result is X is equal to R of P plus Z of P. That is, every element in capital X can be written as a linear combination of written as the sum of an element in R of P and an element in Z of P. Okay, for that choose X element of X. Then we can write X is equal to X plus P of X minus P of X. That is, X is equal to P of X plus X minus P of X. Okay, but P of X clearly is an element of R of P, and X minus P of X is an element of Z of P, because P of X minus P of X is equal to 0. So this element X minus P of X is an element of Z of P. So we have written X element of capital X as the sum of P of X and X minus P of X, that is, elements of R of P and Z of P. Okay, so and since R of P and Z of P clearly subspaces of capital X, R of P plus Z of P is a subset of capital X clearly. So from this we can infer that capital X is equal to R of P plus Z of P. Okay, and the fifth one is R of P intersection Z of P is equal to set to 0. Okay, the common element in R of P and Z of P is the 0 element itself. For that we are checking let Y element of R of P intersection Z of P, then we have to show that Y equal to set to 0. Okay, or Y equal to 0. Y element of R of P intersection Z of P means Y element of R of P and Y element of Z of P. Implies Y element of R of P means Y equal to P of X for some X element of X, and Y element of Z of P means P of Y is equal to 0. Okay, combining this, we can say that P of y, applying P, we can see that P of y is equal to P of x and P of y equal to 0. And combining this, we can see that 0 is equal to P square of x, and P square equal to P implies P of x is equal to 0, and P of x is y, so y is equal to 0. This means that the common element in their intersection is 0. So we have obtained x is equal to R of p plus z of p, and R of p intersection z of p is equal to z to 0. Hence capital X can be written as the direct sum of R of p and z of p also. Okay. Now here is a note. If y and z are two subspaces of capital X such that x is equal to y plus z and y intersection z is equal to z to 0, then for every x element of x, there are unique y element of y and z element of z such that x is equal to y plus z. Okay. Then the map P of x equal to y is a projection called the projection onto y along z. Okay. So here is the proof. So we have y and z are subspaces of capital X such that x is equal to y plus z and y intersection z is equal to 0, z to 0. Then also for every x element of x, there exists y element of y and z element of z such that x equal to y plus z uniquely, in the unique sense. Okay, so we have to prove that the map defined by P of x is equal to y is a projection. Clearly P is a map from x to x, and the map is defined by P of x is equal to y, the element of capital Y. Okay, then P square of x is equal to P of x, which is equal to P of y, which is equal to y, because y can be written as y equal to y plus 0, where y element of capital Y and 0 element of capital Z. So this is the representation of y, and so P of y is clearly equal to y. So this means that P square of x is equal to y, and and y is clearly P of x. So P square is equal to P. This means that P is a projection, and this projection is called projection onto y along z. Okay. Now we have the definition of a closed map. Let x and y be metric spaces. Then a map f from x to y is said to be continuous if xn converges to x in x, then f of xn converges to f of x in y. Then we say that the map is continuous. And the map f from x to y is said to be closed if xn converges to x in x and f of xn converges to y in y, then y equal to f of x. Okay. So if xn converges to x and f of xn converges to y, then that y must be f of x. Then only we say that the function capital F is a closed map. Okay. Clearly every continuous map is a closed map, but the converse need not be true. That is, a closed map need not be continuous every day. A closed map need not be continuous. For example, consider capital X equal to capital Y equal to R, and the function f of t is equal to 1 by t if t not equal to 0 and 0 if t equal to 0. Clearly the function is not continuous and it is closed also. Okay. Now we are going to the theorem 10.3. The statement is, let x be a normal space and P from x to x be a projection. Then P is a closed map if and only if the subspaces R of P and Z of P are closed in X. In that case, P is in fact continuous if X is a Banach space. Okay, so we have to prove that if X is a normal space and P is a projection on X, then P is closed if and only if R of P and Z of P are closed. Okay, so first we have capital X is a normal space and P from X to X is a projection. Suppose P is a closed map, we have to show that R of P and Z of P are closed in capital X. Okay, for that we have to consider sequences yn in R of P and Zn in Z of P such that yn converges to y and Zn converges to Z in capital X. Then to show R of P and Z of P are closed, it is enough to show that converging points y and Z is in R of P and Z of P respectively. Okay. For that, consider the sequence yn in R of P and Zn in Z of P such that yn converges to y and Zn converges to Z in capital X. Okay, since the sequence yn is in R of P, each yn can be written as P of x1 for some xn element of capital X for every n, and Zn element of Z of P means P of Zn is equal to 0 for every n. Okay, then P of yn is equal to P of xn, and that is P square of xn, which is equal to P of xn since P is a projection, and that is equal to yn. Means P of yn is equal to yn and P of Zn is equal to 0. Okay, that is P of yn equal to yn converges to y in capital X by our assumption, and P of Zn is equal to 0 converges to 0 in capital X clearly. Okay, that is yn converges to y and P of yn converges to y, and Zn converges to Z and P of Zn converges to 0. Our supposition is actually P is a closed map. So yn converges to y and P of yn converges to y means y is equal to P of y since P is a closed map, and Zn converges to Z and P of Zn converges to 0 means 0 is equal to P of Z since P is a closed map. Okay, so y equal to P of y means y is an element of R of P, and P of Z is equal to 0 means Z is an element of Z of P. So the converging points y is an element of R of P and Z is an element of Z of P means R of P and Z of P are closed in capital X. Okay, so this is the proof of the necessary part. Conversely, suppose that R of P and Z of P are closed in capital X. We have to show that P is a closed map. So consider a sequence xn converging to x in capital X, and P of xn converges to y in capital X. To show that capital P is a closed map, it is enough to show that y is equal to P of x. Okay, so we are claiming to prove that we are going to prove that y equal to P of x. Okay, so we are considered xn converges to x and P of xn converges to y. Since xn element of capital X, P of xn clearly an element of R of P. Okay, P of xn is an element of R of P, and P of xn converges to y by our assumption implies y is an element of R of P since R of P is a closed subset by our assumption. Okay, the converging point should be in R of P, that is y is an element of R of P. Also, P of xn minus P of xn is equal to P of xn minus P square of xn, which is equal to 0 because P square is equal to P, implies xn minus P of xn is an element of Z of P. Okay, xn minus P of xn is an element of Z of P, and xn minus P of xn converges to x minus y because xn converges to x and P of xn converges to y by our assumption. This implies that x minus y is an element of Z of P because Z of P is a closed subspace, and so xn minus P of xn is an element of Z of P, and that sequence converges to x minus y means the converging point should be in Z of P since it is closed. So x minus y is an element of Z of P and y is an element of R of P. Thus x is equal to x can be written as x is equal to y plus x minus y, and here y is an element of R of P and x minus y is an element of Z of P. So x is an element of R of P plus Z of P. So P of x is equal to P of y plus P of x minus y, means P of x is equal to y because P of y is equal to y since y is an element of R of P implies P of y is equal to y. Also x minus y is an element of Z of P means P of x minus y is equal to 0. This means P of x is equal to y. Actually we need to prove this y equal to P of x. So our projection capital P is a closed map. That is, if xn converges to x and P of xn converges to y, then that y is equal to P of x, means P is a closed map as we said. Okay, so this is the theorem. And we have to prove one more thing. In this case, P is in fact continuous if X is a Banach space. Okay, so assume in this case capital X is a Banach space, then Z of P and R of P are closed, means P is closed in this case, and P is linear also. So by theorem 10.2, the closed graph theorem, if X is a Banach space, and here P from X to X, okay, so X and X are Banach spaces, P from X to X is closed and linear, then clearly P is continuous by theorem 10.2, the closed graph theorem. Okay, so in this case, if X is a Banach space, then the projection become continuous. Okay, that is the theorem. Thank you.